Right, so in the last video we were solving the third exercise and we were somewhere in the middle. We actually assumed that F is injective. Under this assumption, we were going to prove these two things. One of them is this f of A intersection f of B is equal to f of A intersection B, and the other is of course the one involving differences. Okay, so these two things we were going to prove, but we already have proved these. This is a subset of FA intersection FB. This one we already have. So for equality we now have to prove the reverse inclusion. So let us start. So we will start by considering an element in this set. Okay, not in that set, but first of all let us prove the one involving intersection. So there we consider any element in this set FA intersection FB. Keep in mind that now F is injective. So let us take Greek letter, since we have already taken x, y, all those things. So let beta be an element in FA intersection F of B. Then beta belongs to F of A and beta belongs to F of B. This implies beta is equal to F of say alpha 1 for some element alpha 1 in A, and this is the conclusion that we get from this relation beta being in FA. Just like that, from the second one we get and beta is equal to F of alpha 2 for some alpha 2 belonging to B. Now we use these two equations together. Doing that we get F of alpha 1 is equal to beta, which is equal to F of alpha 2, and the fact that F is now injective will imply that alpha 1 is equal to alpha 2, and owing to the injectivity of F, we have alpha 1 is equal to alpha 2. Now look at this. Alpha 1 is an element in A, alpha 2 is in B. But since they are equal, so this common element is in both A and B, that is, it's in A intersection B. Hence, we have this beta is equal to F of alpha 1, where alpha 1 belongs to A intersection B but then beta belongs to f of A intersection B. So any element in FA intersection FB is also in FA intersection B. So this set is a subset of this, and what we have already proved, combining that with this one, we get equality. Combining this with the other containment, we get equality. So that's how, if F is injective, then we get the first equality. Just like that, now we are going to prove the second one. So for the second one, we already have something. What do we have? We have this f of A minus f of B is a subset of this. This we already have proved for us, regardless of what f is, that is whether f is injective or not, it does not matter. This is always true. Now under the assumption that f is injective, we have to prove the reverse inclusion. Okay. So let us do that. So let delta be any element in f A minus B. Then delta is equal to f of gamma for some gamma in A minus B. Okay. Now since gamma is in A minus B, gamma will be an element in A and not in B by the definition of A minus B. This implies gamma belongs to A and gamma does not belong to B. From delta equal to f of gamma and gamma belonging to A, we have this delta belongs to f of A, because delta is the f image or the output of some element in A under F. So that's why by definition of this forward image, delta will be in FA. Now we want to conclude that delta is in FA minus FB. That means delta should not be in FB. So what happens if delta is in FB? What goes wrong? So let us suppose belongs to FB. We will prove that this supposition is wrong by trying to arrive at a contradiction. Then, since delta is in the forward image of B under F, so it will be equal to f of, say, some element epsilon for some epsilon belonging to B. but then we already have delta equal to f of gamma. F of gamma is equal to delta is equal to f of epsilon, and the fact that f is injective would imply that gamma is equal to epsilon, and epsilon belongs to B, so this belongs to B. And this is a contradiction because gamma does not belong to B. This is a contradiction and proves that the last supposition is wrong. And what was our supposition? That delta belongs to f of B, so that means it cannot be in f of B. That is, delta does not belong to f of B. So we now have delta belonging to FA and delta not belonging to FB. So that means delta belongs to FA minus FB. So any element in f of A minus B has been proved to be also in this set. Thus, this is a subset of the second one. Combining this with the already established relation, that is the other one, we get equality. Okay, so injectivity of f gives us equality in both these weaker relations. By the way, I think I forgot to mention one thing. At the end of the solution to the second exercise, we came across an example, right, where we showed that if f is not injective or surjective, then so and so things are wrong. That is the one which involves these things. F inverse of f of s, that thing. Okay, there at the end of the solution you write one line. Note that you write this line. Note that f is that square function, if you remember, fx equals x square. That particular function is neither injective nor surjective. And then you end the solution. So this extra line you write there. Okay, and although we can end the solution here, but just like the second exercise, let us also see here what happens if f is not injective. Then naturally something may go wrong, and that's exactly what happens. Here also we are going to take one particular example. The example will be almost like the one we had in the second exercise. To see what happens or what goes wrong if f is not injective, we considered the following example. Let x, and now x and y are both the same and they are that same set, the previous x that we already had in second example, second exercise. The function is also the same. The formula defining it is same. And now we would need A and B. So A is this set. A is the singleton set consisting of -1 and B is the one consisting of 1. Okay. So for this example, we calculate the sets that we were dealing with here in the solution. Note that the first one involved intersection, so we do that first. If A intersection B, okay, A and B are disjoint, so their intersection is the empty set whose F image is also the empty set, and this is not equal to f of A it's not minus f of A intersection f of B, right? To calculate f of A, we have to take the square of this number, so that gives us 1. Keep in mind that since f of A is supposed to be a set, although we have a single number here, but we have to write it as a set. We cannot write f A is equal to 1, that would be wrong. Squaring this one also gives us the same set. So the intersection is this singleton set, and these are not equal. So in this case, equality fails, and just like that, let us now see the difference. F of A minus B. Okay, since A and B have nothing in common, so f of A minus B is f of A, that is A minus B equals A, and f of A we have already seen equals this. However, this is not equal to FA minus FB, which turns out to be the empty set. Note that, okay, here why are these equalities failing? It's because f now is not 1-to-1. F maps both -1 and 1 onto the single element 1. Note that f is not 1-to-1 or not injective, same thing. And this ends the solution to the third one. Okay, so now we move to the fourth one. So the third one shows that as far as direct as far as direct or forward images are concerned, forward images don't behave so well with respect to the set theoretic operations. However, the next one involves a similar exercise which is about the inverse images. Now, I think I have already said this in the last video. Inverse images behave surprisingly well. There, whether you take union, intersection or difference, you always get equality, and that's what we are going to prove now next. So this is the fourth one. Let f from x to y be a function. Thus starting is same, be a function, but now instead of considering subsets of the domain, we are going to consider subsets of the range. And let u and v be subs. Okay, let me write from here. This be subsets of the range y. Show that f inverse of u union v equals f inverse of u union f inverse of v just like that. In case of intersection, we have equality. And that f inverse of u minus v equals f inverse of u minus f inverse of v. Okay, so here in this case there is no exception. We for all of them we have equality. So I'm not going to say much since we have already seen one such exercise. I'll just do the steps. So first we prove the union. We can in fact proceed just like the previous solution. If you remember, we started the solution like this. If C and D are two subsets of the domain and C is a subset of D, then that implies f of C is a subset of f of D. A similar thing is true for inverse images, and that I am going to mention. You prove that for me. It's easy to prove that for two subsets C and D of Y, if C is a subset of D, then that implies f inverse of C is a subset of f inverse of D. Okay, and we are going to use this just like how we used the other one in the previous solution. And we can be a little brief, more brief than the previous solution, since okay, what should I, okay, u intersection v is a subset of u and u is a subset of u union v, and u intersection v is also a subset of V, and that is a subset of U union V. We have these things. F inverse of U intersection V is a subset of F inverse of U, that is a subset of F inverse of U union V, and this thing. Okay, from these final relations, we can conclude these two things. These imply that since F inverse of U and F inverse of V both contain F inverse of U intersection V, so their intersection will also contain this. This imply F inverse of U intersection V is a subset of F inverse of U intersection F inverse of V. Just like that, both these sets are contained in this set, F inverse of U union V. So their union will also be contained in this set, and F inverse of U union F inverse of V is contained in this inverse image of the union. So you see that for the first two equalities, for each one of them, one part is now available to us. We have to prove the other parts by considering elements. Next, okay, we should not write next, I mean this is not over yet. So we first try to prove the opposite of this containment. That means we are going to take an element here and prove that it belongs to this set. So okay, now this is a new solution, so we can take X. Let X be an element here, F inverse U intersection F inverse V. Then X belongs to F inverse of U and X belongs to F inverse of V. This implies, by the definition of inverse image of a set, Fx belongs to U and Fx belongs to V, or Fx belongs to U intersection V, okay, because it belongs to both the sets, and hence X belongs to F inverse of U intersection V. So any element in this set is also in this set. Hence intersection F inverse of V is a subset of this. Combining that with this one, we get equality, and we get Now, if you have been noticing these solutions attentively, you can see that just like that, we can also prove the opposite containment of this one. You repeat this whole thing starting from this, replace intersection by union everywhere, and you get the other thing. So that part I am leaving out. Okay. Similarly, these places where I write it can be, it's easy to prove that similarly, it means you have to do it for yourself. Similarly, we have, we can write equality at once, but let us write the opposite relation of this one. Union V is a subset of this, and hence so the first two equalities have been proved. Now we take the last one. Next, let, so it's just like that, we consider an element in this set and we prove that element is here, and the converse also. Next, let, what can we take? Let us take B or A. Let A be any element in F inverse of U minus V. Then F of A belongs to U minus V. Okay, let me, instead of writing phrases, let me use mathematical symbol, that will be much more neat. So this implies F of A belongs to U and F of A does not belong to V by the definition of difference, and that implies A belongs to F inverse of U, and A does not belong to F inverse of, okay, this is clear. It comes from the definition of inverse image of U that A belongs to F inverse of U if and only if F of A belongs to U. But what about this one? Does this thing imply this thing? Yes, but how? Let us see. You see, if we write what this symbol means, it's just this. F inverse of V is the set of those elements in the domain whose F images belong to V. Another way of writing this statement is this: for any, or let me write, for all x belonging to x, x belongs to F inverse of V if and only if fx belongs to P. That's because this is the meaning of F inverse of V. So that means if a, okay, let me just break it down further. This actually has two implications, right? One of them is this: F inverse of V implies fx belongs to V. and the other one is the opposite one. Fx belongs to phi implies x belongs to f inverse of phi. Okay, now here what do we have?